Hello, this is the Physics 2211 Lab 1 for constant velocity. So here's my table of contents. We're going to have an introduction, then all of this. Our purpose is to observe the motion of an object that is moving at a constant velocity with zero acceleration, and we're going to compare the movement of the push marker as it rolls over some distance in the experimental design using tracker and a computational model in GlowScript. We're going to be assuming that there are no net forces acting on the object, no friction, no air resistance, a flat surface, and no acceleration of any kind. Our fundamental principles are going to be Newton's first and second law, his first law being that an object in motion stays in motion unless acted upon by another force, and his second law stating that the relations between the interactions of the systems and the surroundings change the momentum of the system, and it's all related. So we're going to use two equations, the velocity update and position update, and we'll get to those in a second. First, we're going to start with our experimental design. The marker will be moving at a constant speed and direction, and the marker is the system. The surroundings include the force applied, gravity, and friction, but they're all assumed to be negligible. Observational data is gathered using the tracker app, and the computational gathered using GlowScript app. Both trials start at 0.0 meters and 0.0 seconds. We're going to be using the velocity update formula given by F net equals the change in momentum over the change in time. Then that's reinterpreted to be the final momentum equals the initial momentum plus F net delta T divided by mass gives us our velocity update formula. F net is known to be 0 because that's what we're essentially doing here. So that's going to give us this nice equation. The velocity final equals the velocity initial. So we'll be using that later. Next, we're going to use the position update. Since we use VF equals VI, we can use VI in our position update formula instead of using the velocity update and then inserting that into the position update. So the velocity derivative is position, change in position over the change in time, rearranged to be velocity times change in time equals the change in distance. And we finally get our position update formula. V average times delta T equals change in position. Here's a quick model of the tracker app. As you can see, the marker is flicked, and then we track the marker's path across here. And if I can bring it back here, you can see the data compiled in this bottom right corner and a graph being presented in the top right corner. So this is going to be position over time, position over time there. Next is going to be our tracker data. The marker was captured at to be 0.02 meters or 2 centimeters. The motion is captured at 30 frames per second. The initial position of the tracker was 0.00 of 00 for XYZ directions. The initial position in GlowScript is also 000. Since the ball is moving left to right and the positive axis, x-axis is time and the y-axis is position, you can see this position over time graph as a positive linear slope. And this is my tracker data. So the tracker data, to find that graph, was put into Excel file in graphical form. That tracker data that was put in the bottom right corner was given this. And from this, we're actually going to get our computational model estimation. So to do this, we're going to use the velocity update, velocity average equation. So that's just going to be the change in position over the change in time. Since position and time were both initially set to 0, we can just use our final times over position to get our velocity average. So we're going to be using 0.33 meters here divided by 0.4 seconds, giving us an average velocity of 0.825 meters per second in the positive x direction. Next, we're going to use our GlowScript computational model. This is my code right here. Line 35 shows the initial position being 0, 0, 0, then the initial velocity being 0.825 meters per second. Then you can see in line 56, F net acting on the vector is 0, which is what we're solving for here. Line 60 shows that that VI equals VF that we talked about earlier. So that the initial velocity is going to equal the final velocity. There is no update in the force, so there's no velocity update. For our position update right here, you can see it's just position plus, it's just the initial position plus the ball velocity times time equals the final position. So 0 plus 0.825 times the time equals our final position. So this is just that last formula. Finally, we're going to take our comparison here. So our orange line is our observed tracker data, and the blue line is the computational model. As you can see, the orange line has a slight deformity, and this is because the real world can't actually have a 0 net force. So there are some forces acting on it causing an irregular slope, while the computational model is perfectly straight because there's no outside forces acting on it. Finally, what ifs. When analyzing the video, it was decided that the orientation of the vector would be in the positive x direction. So what would happen if x was changed with negative x? So the results would show a negative slope because the object would be moving in the negative x direction. However, the data would coincide because the absolute value of the slopes would be equivalent. So we'd have the same slope, just negative. What does it mean? Because there's no way to identify the total pushes and pulls required to equate the zero net force in the procedure, in the real world, we are not able to attain a true constant velocity through observation in the real world. This is because of external forces like friction and surface deformities causing more friction. So the computational model completely removes these forces and sets the net force equal to 0, and that's how we're able to see the difference between the tracker and the computational model. Thank you.